In this demonstration, I've got a beaker of copper 2 chloride. It's an aqueous solution, so the solid was dissolved into water. And I've also got an aluminum can, a Pepsi can, okay? And all I'm going to do in this demonstration is I'm going to take the Pepsi can, my source of aluminum, and I'm going to add it, I'm going to try to push it down, and even maybe start filling up the can with some of the copper 2 chloride. Now this is a chemical reaction that takes a while, and so we're going to let this just kind of sit, and we'll come back to it in a couple minutes and see what has happened. So a few minutes have passed since we started putting the Pepsi can into the copper 2 chloride. And one thing that I'm hoping you can see right here is that some kind of red solid is starting to form, and it almost looks scraggly, like it's falling off the bottom of the can. I'm going to knock it just a little bit. Oh, can you see that? Look at those chunks of red stuff that are falling off of there. Stop and think about, what do you think that is? It's obviously a solid. Well, we had aluminum coming in, and the other reactant was copper 2 chloride. So in a single replacement reaction, the aluminum and the copper that's in the copper 2 chloride, they're going to switch places. So the metal and the metal ions switch. So we've got copper metal that is starting to come out and land on the bottom. And I'm not sure if you can notice this, but the color of that blue solution is actually starting to fade. So as the copper ions are taken in and turned into copper atoms, we're actually creating aluminum ions. The aluminum metal is actually turning into aluminum ions, which do not have a color when they're dissolved in water. And so we're going to start to see that blue color fade a little bit as the chemical reaction continues over time. In this section, we're going to focus on single replacement reactions and how to predict the products. A single replacement reaction can be described as having two reactants on the left and two products on the right. Specifically, the reactants include one element and one compound. The compound is often dissolved in water. On the right-hand side, we also have a new element forming and also a compound that is frequently dissolved in water. If we wanted to use letters to describe a single replacement reaction, we could describe the element as A and the compound as BC. Notice in the chemical reaction that A and B are switching places. In many of these reactions, we will see A as a metal. B is a metal ion. In these chemical reactions, A will kick B out of the compound and replace it. In other words, A and B switch places. Visually, we can show this with circles. Notice how the blue circle kicks out the yellow circle. In the demonstration that you just saw, an aluminum can was placed into a solution of copper 2 chloride. In this chemical reaction, the aluminum was a solid and the copper 2 chloride was an aqueous solution, and that's very common for the different types of single replacement reactions that you will see. It's always good to do your word equation ahead of time, so stop and think about what are the names of the products before you ever start looking at the formulas. If aluminum is the element that we added, we know that that's a metal. If this reaction works, which we know it will kick out the copper 2 ion that's in the aqueous solution. Therefore, the products of this chemical reaction are copper, which we saw as the reddish brown solid that was coming out of the solution. And the solution that's left behind is aluminum chloride. In the video, you may have noticed that the blue copper 2 chloride that we had in the beginning, that solution starts to fade very slowly in color. And by the end of the reaction, that blue will completely be gone and we'll be left with a colorless solution of aluminum chloride.
let's look at the formulas. Aluminum we know is Al, and it's in the solid state. Notice there's no charge on the aluminum because it's an element. Copper 2 chloride is an ionic compound dissolved in water, which we will describe as CuCl2. We do have to use some good formula writing skills to do that. And on the product side, we have copper metal coming out. And then the solution of AlCl3 is also on the product side. We can also balance that equation, and now we are completely done. One of the most important things that you need to know about single replacement reactions is that not all of them occur in nature. In other words, just because you can write a single replacement reaction doesn't mean it actually will happen. So I would like to take the reaction that we just looked at a moment ago in the demonstration, and of course we knew that this one worked because we did it. We saw the aluminum can breaking down, and then we saw the copper metal starting to come out. What I would like to know is what would happen if we took what we now currently see on the product side, which is copper, and what if we took a piece of copper and we threw it into a solution of aluminum chloride? Would it work? Now, one of the ways we can figure this out is we can actually do it in a laboratory, and we can determine if the copper starts to break down in aluminum chloride. But when we look at all of these single replacement reactions, you're not going to be able to do all of them in a laboratory. You just don't have time. So how else can we do it? There's a chart that I'm going to show you in a minute. It's called an activity series of metals. What it does is it ranks all the metals in terms of their reactivity. On the chart, you are going to see up at the top the most reactive metals in nature. And at the bottom of the list, you're going to see the precious metals, the metals that we often use in things like wedding bands. These are metals like gold and platinum and silver. And when we take a look at this list, what we're going to learn is that copper is less reactive than the aluminum metal that we see in aluminum chloride. And when that happens, when the metal that you throw in is less reactive than the metal that's already a part of the compound or a part of the solution, we learn that the chemical reaction simply cannot happen in nature. It will not be spontaneous. This is the list that I was talking about. It's an activity series of metals.
This is a list of a whole bunch of metals, and on the top, up in this area right here, this is where we see the most reactive metals, and then way down low, you'll notice that gold and platinum and many of those very expensive metals that we use in wedding bands and fancy jewelry, those are shown down on the bottom. And so what we see is this list is going from the most reactive up at the top in this sector, and when we get to the bottom section with silver and platinum and gold, that's where we see the least reactive of the metals. I want you to notice where aluminum is. Aluminum is right here. And copper is way down low on this list, way toward the bottom, okay? So what we know is aluminum is more reactive than copper.
Now I'd like to practice a few single replacement reactions and see how you do. Remember, in all of these, I want you to think about what element is being thrown in, and then use an activity series of metals chart and determine, is the element that I'm throwing in more reactive than the positive ion that I'm trying to kick out? If it is more reactive, then the chemical reaction will occur. If the element that I'm throwing in is less reactive, then the chemical reaction will not occur. Some things that I want you to keep in mind as well are, don't forget about all those good formula writing skills that you've worked so hard on. You do need to consider charges on ionic compounds and always make them neutral. In addition, try to determine the states of matter on the product side. In this particular reaction, we have solid magnesium being introduced to a solution of hydrochloric acid. The magnesium is trying to kick out the hydrogen, but will it work? When you look at an activity series of metals, you'll find out that magnesium is higher on the chart than hydrogen found in an acid. In other words, it's more reactive. And so in this particular instance, the magnesium has the ability to kick out the hydrogen. The magnesium will now be a part of the solution, which we will call magnesium chloride. This is an aqueous solution. And what's interesting here is the element that pops out is hydrogen gas. I've written it as H2 because hydrogen is a diatomic element. Always remember to go back and balance your equation when you're completely done. The second example involves magnesium and water. I've written water as HOH. It's often easier in single replacement reactions to consider the water as a combination of a hydrogen ion and a hydroxide ion. If the element is going to kick out the hydrogen, it will replace it, and then that element will be connecting with the hydroxide ion. In this particular instance, though, when we look at the chart, we find out that magnesium is actually lower on the chart, meaning it is less reactive than the hydrogen that we find in water. That means it does not have the ability to kick out the hydrogen, and therefore this chemical reaction will not react. Again, the magnesium was less reactive than the hydrogen you find in water. This will not spontaneously occur. So now we're going to take a look at several single replacement reactions, and as you look at these, I want you to use your activity series of metals chart and try to figure out if these happen. This might require you to stop the video. If it seems like I'm going too fast, stop the video, take some time, think about the activity series of metals, work on your formula writing, and if the chemical reaction does occur, use your ion charges to make neutral ionic compounds if those are part of your products. And at the very end, you'll go back and you'll balance your equation. Here comes our first one. Lithium, solid lithium is added to water. Take a moment and think about it. Can the lithium kick out the hydrogen that you see in water? It absolutely can, meaning we'll be left with the solution of lithium hydroxide, and then the hydrogen is kicked out as the elemental form of hydrogen, which is H2, and that would be a gas. Our second example involves zinc being placed in a solution of silver nitrate. Take a moment, think about it. Can the zinc kick out the silver that we see in the silver nitrate solution? It definitely can. Therefore, the zinc now combines with the nitrate. Using our ion charges, we form zinc nitrate, and solid silver would be our other product. The third example involves gold being added to a solution of silver nitrate. Now you can use your chart, or you can actually use your common sense. Think about these two metals. Gold is often used in wedding bands. Even though silver is often used in jewelry, you've probably seen it tarnish or darken, meaning it does react with oxygen over time. It's a little bit more reactive than gold is. So again, going back to how we do this, the gold we know to be less reactive than silver. Therefore, it cannot kick the silver out, and therefore there is no reaction in this single replacement. I'd like to summarize what we just talked about with that activity series of metals because it's important that you know how to use it. So I've got 3 questions that often come up from my students, and I want to give you good examples and just some notes that you can take down that will help you out in the future. The first question says, what happens if the metal you throw in is more reactive than the metal ion that's already a part of the solution or the compound? Just to review, that means the reaction would occur. And I'm giving you an example here that shows kind of how that works. In this case, the barium is more reactive than the copper, and then therefore it would kick it out. The second question is, what happens if you throw in a metal and that metal is less reactive than the metal ion that's already a part of the solution? Well, in this case, we said the reaction does not occur. To give you an example of this, you could think about copper being added to a solution of zinc nitrate, and the copper is a very stable element. It's not very reactive, and it's less reactive than the zinc, therefore this does not occur. The final question on this page talks about what happens when metals are placed in water. How would you know if the chemical reaction occurs or not? So we know that it depends on the metal's location on that chart. For this chemical reaction to work, the metal must be more reactive than hydrogen in water. An example of that would involve sodium, which is an alkali metal. When sodium is placed in water, a very explosive reaction occurs. However, if we were to consider copper being placed in water, copper is used in electrical wiring in our homes. It is not a very reactive metal, and it's not able to kick out the hydrogen that's a part of water. Therefore, there's no reaction. On this page, we're going to move very quickly, and I would strongly suggest that you pause the video after each one and stop and think about it before you show what the answers are. But we will move very quickly. At the end, I will balance all of these equations for you so you can check to see if you're doing your balancing correctly. Our first equation involves gold being added to a solution of potassium nitrate. Take a moment and consider if this reaction works or not. If it does not work, simply write no reaction. If it does work, consider what the products would be and write them correctly. If you said that there's no reaction, you would be correct. Gold is a very stable metal. It cannot replace the potassium ion. The second example involves zinc being added to a solution of silver nitrate. Take a moment, consider whether or not this reaction would occur, and if it does, write the products. If it does not, write no reaction. If you said this reaction occurs, you would be correct. The products are zinc nitrate and solid silver. The third reaction involves the alkali metal lithium being added to water. Consider the two reactants. Does it work or not? This reaction would definitely occur. Lithium is able to replace the hydrogen in water. It connects with the hydroxide to give us a solution called lithium hydroxide. Hydrogen is kicked out as the element H2. Our next reaction involves solid copper being added to a solution of iron 2 sulfate. Stop and consider if it occurs. If it does, correctly write the products. If it does not, write no reaction. This chemical reaction would not occur. Copper is too stable of a metal. It cannot replace iron in the aqueous solution. Our next reaction involves copper being placed in water. This chemical reaction does not occur. As we mentioned earlier, copper is very stable. It will not replace the hydrogen that we find in HOH. The last example on this page involves sodium metal being added to a solution of hydrochloric acid. Stop and think about it. The chemical reaction does occur. The sodium will kick out the hydrogen and replace it, leaving us with an aqueous solution of sodium chloride and the element hydrogen. Going back and balancing all the equations would look like this. You definitely want to make sure you balance the equations when you've predicted the products correctly. On this next page, I've given you 3 single replacement reactions that involve acids. I've also written them as word equations to give you a little bit of practice taking the word equations and creating formula equations. Our first example involves magnesium being placed in hydrochloric acid. Our reactants, we would write Mg and HCl. Stop and think about if the magnesium can replace the hydrogen in the acid. It absolutely can, using good formula writing. Mg with a positive 2 and chloride with a negative 1 would give us MgCl2 as one of the products, and the element hydrogen is the second product. In the second reaction, sodium metal is placed in phosphoric acid. Take a moment, think about the positions of these two on the activity series of metals. The sodium is able to replace the hydrogen found in an acid, leaving us with sodium phosphate in the aqueous state and the element hydrogen. The last one on this page involves copper being placed in hydrobromic acid. We've already seen several examples of copper being used, and we know that it's a very stable element. And in this particular case, again, the copper is too stable for this chemical reaction to occur. There is no chemical reaction. So finally, I want to talk to you a little bit about single replacement reactions that don't always involve a metal being added to the solution. What if you were given a non-metal and asked what would happen in this particular single replacement reaction? Well, in all the other ones, we had a metal replacing a metal ion or a metal replacing a positive ion. If you are given a non-metal, they occur in a very similar way, but we know that the non-metal would replace another non-metal, and that is a non-metal that's already a part of the solution. We saw that activity series of metals chart, and we were able to rank the most reactive metals and the least reactive metals. But what happens when you're dealing with non-metals? Down on the right-hand side, I'm just going to show you a little tiny reactivity chart, and this involves the halogens. I've ranked them from the highest on the top all the way down to the least reactive halogen on the bottom. Fluorine I often refer to as the beast of the elements. It is the most reactive halogen, all the way down to iodine on the bottom, which is the least reactive of those four. Let's look at three scenarios and see if you can decide what happens in these single replacement reactions. The first of these is an example where fluorine is shown as an element. Fluorine is a gas. It's being bubbled into an aqueous solution of sodium chloride. For this chemical reaction to occur, the fluorine would have to be more reactive than the other non-metal, in this case chlorine. Can fluorine kick out the chlorine and replace it? Well, the fluorine is more reactive than chlorine, so we know the answer to that is yes. Fluorine is going to replace chlorine. It's going to leave us with a solution of sodium fluoride. Again, consider your ion charges before you try to write that. And the element chlorine will be kicked out by itself. There are the products of that chemical reaction. Here's a second example. This time bromine, a nonmetal, a halogen, is being introduced to a solution of sodium chloride. For this chemical reaction to happen, the bromine would have to be more reactive than the chlorine. But if you look at the chart, that's simply not true. Bromine is less reactive than chlorine. Therefore, this chemical reaction cannot occur. The third and final example is chlorine being added to a solution of potassium iodide. For this chemical reaction to occur, the chlorine would have to be more reactive than the iodine in the compound. So stop and look at the chart and think about who's the more reactive of the nonmetals. Chlorine in this case is more reactive. Therefore, it has the ability to switch places with the iodine. We'll have a compound called potassium chloride as one of our products. Think about your ion charges before you try to write it. And iodine will be produced as an element as the second product. It would look something like this. My final step is to always go back and balance my equation. This completes our tutorial on single replacement reactions. Please join me for the next lesson, which involves double replacement reactions. I hope you found this tutorial to be very useful. Thanks for joining me.